Welcome to ALD Stories, a series chronicling the personal journeys of the people behind atomic layer deposition, untold stories of the technology, and deep dives into the history, development, and future of ALD. I'm your host, Tyler Myers, bringing you this podcast from Benek, the home of ALD. Welcome back to a new year of ALD Stories. We start off 2024 with a well-known face in the German ALD community, Professor Martin Knaut. Martin is a professor and chair for the Institute of Semiconductor and Microsystems Technology at TU Dresden and the Atomic Layer Processing Group leader. He's also a founding member of the Atomic Layer Process Innovation Network, or ALPIN, organizer of the annual ALD for Industry event, and runs a small in situ tool development company called ALS Metrology. With a long career working with ALD in Dresden at the likes of Infineon and Qimonda, Martin has witnessed the ebbs and flows of the semiconductor industry in the state of Saxony. In this episode, Martin and I discuss the goal of the Silicon Saxony organization, how we can better recruit students in microelectronics, and why he originally started the Atomic Layer Process Innovation Network. We also discuss his company, ALS Metrology, the importance of using in situ monitoring for process development, and his work on flash-enhanced ALD. Martin and I had a really wonderful conversation ranging the full spectrum of topics available when discussing ALD. It was a pleasure to have him join ALD Stories, and I extend a huge thanks for his time and willingness to contribute so soon after meeting me. So with that, please grab your tea or coffee and enjoy TU Dresden's Martin Knaut. Good. Well, hey, Martin, thank you for joining and welcome to the ALD Stories podcast. It's really nice to have you here, and I'm excited to discuss some of the work that you do at TU Dresden and just talk about Dresden in general. So welcome to the show.
Thanks, and I'm also enjoy being here, so looking forward. Let's see.
Good. So as is tradition on this show, we usually just start talking about your background a little bit and how you found yourself working in ALD, what kind of drew you to it and what kept you there. So if you could go ahead and give us a little bit of an idea how you found yourself in this field.
So I started with my studies in electrical engineering in 2000. And because I wanted to do something which was related to engineering, and then I decided, electrical engineering sounds fine. And and during my studies, there's some time where you have to decide which direction, which field you want to be in, and then I decided, microelectronics sounds somehow interesting, and is sounds also useful because Dresden already at this time was a microelectronics hub, and with some big companies and smaller ones and so on. And I said, so microelectronics seemed to be useful in Dresden, and that was the start, which brought me to the ALD world, because then I had to find a topic for project works later on, and so on. And I checked what was available at the institute, and then I saw something with ALD. So I started this together with a friend. So he was doing ALD processes in a new self-built ALD tool we had here in, I think, something like 2003 or 4. And I was doing the XPS analysis of the films and other stuff, so mainly the metrology. And this was the start. So then I never left the ALD world again. So then after that, I had some internship at Infineon, also dealing with ALD films and their film properties. So mainly film stress measurements and how process parameters affect film stress, so which was a big topic at this time there. And then, I finished my diploma also with an diploma thesis which I have done at Infineon, because at this time it was already Qimonda, so they changed the name and split the DRAM part from the main company and called it Qimonda. So I did my diploma thesis there, and then fortunately I went back to university to start working at the university, because 2 years later Qimonda was bankrupt, and then it was a good choice to not stay there. Also, they asked me, of course, for that. And so at this time I've been already in ALD a lot, and mainly, and I still am there.
It's interesting that you said it was like 2003 that you kind of started doing ALD stuff. That's pretty early on.
Yeah, right. So at this time, I think Infineon was also starting with that topic, and then we had some joint projects, or at the university have a joint project about this topic. So with Infineon, and this was the starting point for the ALD work at our institute. So yeah, there was uh, someone who was pushing this. We did at this time, I think, mainly solar stuff and also some CVD and PCVD, and then they decided, oh, ALD might be an interesting topic, so Infineon is interested in it, and it's something new, and yeah, this was the starting point. And there was an self-built tool and another, I think, a PCVD tool, which was changed in a way that it can be used for ALD, and yeah, this was the starting point. And yeah, you're right, it was quite early, let's say. Yeah.
Yeah, I guess good place to be, Dresden. Then, if it was already microelectronics hub, that kind of naturally a place that ALD was probably going to thrive at some point.
Yeah, of course. So this was a good place for that. And yeah, there had been some, let's say, more difficult times in the past, also for Dresden and microelectronics. So when we lost Qimonda in, I think it was 2008 or so. So especially the politics decided that microelectronics is something which is not really important, and that you can buy all the stuff cheaper in Asia. And so it would have been easy to give some money to Qimonda, and they would have survived. And they really did these leading edge technology stuff, which was, after that, it was, yeah, principles was gone from Europe. So there's nobody doing this leading edge stuff anymore, like Samsung or TSMC is doing. So Europe lost some important part in the microelectronics industry with that. And so now, of course, yeah, they try to spend a lot of money to have Intel here, or maybe TSMC and so on. But it's much more money, of course, than having it spent 10, 15 years ago, and having their own company doing this here. Yeah, but at the end, or at the moment, it's fine. So at the moment, the politics is aware of the problems with microelectronics, and that you cannot buy everything in Asia every time. So Corona and all the problems afterwards showed that it's maybe better to have also some own production in Europe, and that's the university always thought that is, yeah, not really an important topic for the university, and there wasn't much support and so on. But this changed in the last years. So yeah, so there are now already things going on together with South Korea and or with TSMC and so on. So the university is trying to push microelectronics a little bit further. So which is good. So we are happy about that.
It's nice.
Yeah.
Glad that they kind of turned the thinking around at some point. I imagine, in the past 10 years, somebody in Saxony was kicking themselves, like, how could we have let that company
Yeah, of course. Many people say this, but at this time, the people who decided this or just said, okay, we don't need this. So we asked somebody, and they told us we can buy this in Asia cheaper. And then it was the decision, yeah. So a lot of people didn't
short-term
understand
solutions.
Yeah, right.
Yeah. I know that there's kind of the play on the Silicon Valley, but there's the Silicon Saxony organization. Right?
Yep.
Is this something that has been around for a while, or was this something new in like the past decade?
I would think. I mean, it's already old, so it's there for a long time. But I cannot tell when it was founded. Can look this up, but it's there already since I'm not sure, maybe 20 years or so. So really since a long time. Maybe it was even earlier. So my former professor was one of the founders of that, or he was involved in the founding of the Silicon Saxony. Yeah, and the idea was to have something which is similar to Silicon Valley, so a big network of companies and universities and institutes to improve the collaboration and discussions and everything between all of them. Which is of course important if you want to do microelectronics. No, there's not a single company who is capable of doing this, so you need a lot of suppliers and companies, and of course you need also a lot of institutes or universities, which to take care of the education of the students and so on, because you need the people, and this is not that easy to find some of them, which is also a big topic at the moment. So all the companies recognize that it's hard to find people for their business.
There are a few people I've talked to on here that we have been trying to push, like, hey, if you're interested in semiconductors or microelectronics, like, go study it, because we really need you right now.
And it's somehow difficult. So I can remember it was maybe something like 10, 13 years ago, maybe after the bankruptcy of Qimonda. So the topic microelectronics was not really a hot topic, and nobody wanted to do that. So from the whole studies of electrical engineering at our faculty, there are, I think, 5 fields that students can go into, and microelectronics is one field. And in that year, just 2 students decided to go into that field of microelectronics, and this splits again into a semiconductor technology, chip design, and so on. So it was something like nothing, so nobody did it. And so this was maybe the lowest point in the numbers of students, but it's still not really on a high level. So there are not so many, let's say, German students doing this, but we have an international program. So for an master program for nanoelectronic systems, as it's called, and this is something which is indeed growing. So there's every year a growing number of students, but they are mainly from India, China, maybe the Arabian countries, something like this. A few from Europe, of course, a few from Germany, but mainly from abroad. And there are still people interested in being engineers for microelectronics. So, but in Germany it's hard, and I think as far as I know, it's the same in US, and also in even in a country like South Korea, where people think, okay, the microelectronics is very important. They are all in Taiwan, and still, and even there, the university has problems to find students who want to study something in this field.
Yeah, I think even people I know working in ALD and working in deposition and these types of fields are natural people to go into microelectronics afterwards still finish their PhD. I mean, myself included, I'm in a marketing position now and don't see the value, at least, in going to be an engineer in one of these companies and this field, which is a shame. But it is, I mean, it's demanding work and it's tough, and it's geopolitically odd to be in it as well. So yeah, it's a hard sell sometimes. But do you find that all the new activity in Dresden, for example, like TSMC coming there eventually, and these things, is there like an injection of interest from students in Germany now?
It's still hard to say. So, I mean, as I said, there's this English study program, and there is some big interest, especially because people from India or so see this as a great possibility to be an engineer and to find a global company which they can work at, and so on. For the German students, I think it will be like this, but it's maybe takes some time. So typically the problem is you always have to convince them in school, because after school they have to decide what they want to study, and as long as in the school there's no awareness of this field, so that they can study something which is related to microelectronics, then it takes some time until the new students or the former pupils are aware of that there's some possibility to study something which is related to microelectronics, and that is easy to find a good job, a well-paid job. So so at least my students or the last students who finished their thesis here, or as long as I wasn't able to convince them to stay at the university and do their PhD, they started working somewhere else at a big company mainly, and then also are paid very well and so on. And yeah, so in principle, if you are finishing school and you are not sure what to do, and this is of course a good choice, but maybe most of them don't know.
Yeah, I think that's probably the case. I mean, it reminds me of when I was in secondary school. I mean, this was now 10 years ago, but we I grew up in upstate New York, and there is some amount of like semiconductor hub there as well. Intel is there, IBM was there for a while, the ALPIN Nanotech campus, Global Foundries, for example. And I was having a conversation not that long ago with someone who works in like the Department of Commerce for New York State, and I was telling them like I had no idea that this was a thing that was happening like right under my nose, and I don't think a lot of people, myself or like other than myself, knew as well. And even when I was in my bachelor's program, again, just like no awareness at all for this huge industry and hugely impactful industry as well. It's like if that's awareness was maybe raised a little bit more, you have to. Don't want to use maybe the word groom, but plant the seed a little bit earlier, perhaps.
Yeah, so especially in school, I think so. Have two sons, and the older one is already in the 9th grade, and up to now there was nothing like that they somehow realized that there's a microelectronics industry and this would be a good field. So there was some requests exactly from his school, and I was happy about it. And then I sent what we can do together, and that we can give some talks about different topics and so on. But yeah, it's already a year ago and nothing happened. So because there are 28 kids in the class, and the teachers are really busy and so on, so nobody has time to take care of these extra projects. And but I'm somehow optimistic at the moment. So with TSMC, the big fabs which are already in Dresden from Bosch and Infineon and Global Foundries and Intel in Magdeburg and so on. So I think there is some new awareness of that topic, and this at the end it will help somehow. Yeah, let's see how much, but it will help, of course.
Absolutely. Yeah, speaking of you like going to give a talk or giving some information to some schools, I would like to touch on some of the like outreach that you do just in the ALD community, because you are a very active member in organizing events for the ALD people in Germany and atomic layer processing people. Could you talk a little bit about some of the organizations that you work for and have started?
Yeah, so we started with something we called ALD Lab Dresden. So it was, I think, in 2010. So there have been already some groups in Dresden doing ALD. So one was at the Fraunhofer CNT, one at our institute, and the NAM Lab, which is directly next to our institute. And so we decided, let's call it like a network, or we called it ALD Lab Dresden, and to do some things together. And I mean, we have been collaborating before already, but this was the point where we decided, okay, maybe we can start some joint projects, and maybe we can have some meetings to discuss what everybody is doing and what new topics are. And then it didn't take long, and then more groups joined. So because of the microelectronics industry, there have been already a few research groups dealing with ALD, or at least they have been using ALD. So there are also groups doing something completely different than microelectronics, but they simply need an aluminum oxide film sometimes, and then they bought an ALD tool and used it without doing any ALD research. But of course, it was also planned to have them involved so that they learned something about ALD. Also, they are just using the process. And yeah, it didn't take long. Then colleagues from Chemnitz joined, and from somewhere else. And then we decided, I think in 2016, okay, there are so many people from somewhere else now. We have to call it ALD Lab Saxony, because it's not ALD Lab Dresden anymore. Yeah, and then in 2021, we decided together also with another, let's say, network from the Fraunhofer community that we have to call it somehow more general or more German, so not Saxony anymore, because there have been a lot of groups joining from far west part of Germany, and so it wasn't Saxony anymore. And then we decided to call it ALPIN, so Atomic Layer Process Innovation Network. So someone came up with that idea, and since I like mountains, I decided that's a good choice. And then I organized the first, let's say, big workshop of this network in 2021. And it was very lucky because we have been in a time slot between two Corona or COVID waves, or how it's called. So we have been able to do this workshop 2 weeks earlier. It wasn't possible, and 3 weeks later also it wouldn't have been possible anymore. So and everybody was really happy to be there, because they haven't been allowed to go to any workshops or conferences since a year or more than a year. And yeah, it was really successful. So it was right at the beginning. So the first workshop with something like 70 or 80 people from everywhere in Germany, and already there somebody from Austria. And so it wasn't again Germany anymore. So the idea was, I mean, there are ALD conferences like the AVS conference and so on, but so the costs are really high. So if you have a conference in the US, if you want to go there from Germany, you have to pay the flight, the hotel, the conference fees. I mean, you have to spend 3,000-4,000 euros, and there are a lot of groups with just a few people doing ALD, and there's simply not enough money for traveling like this. I mean, sometimes one of them is able to go there. Often it's just a professor, and the PhD students are not able to join such a conference. And so the idea was to have let's say, low-cost workshop. So there are, up to now, we don't have any conference fee or workshop fee. So the idea was to have low level costs. So the best thing would be just travel costs, no costs for the conference, and then we are using sponsors to get the money for the catering and what else is needed. And yeah, so the feedback was quite good. So there are a lot of people joining. So there are sometimes groups attending with 15 people because it's possible for them. So the conference fee isn't there, so they can just join all together, and everybody gets in contact with new people and can do networking and learn something and so on. So I think that's a good thing we started there. Yeah. And yeah, the second thing is the ALD for Industry workshop, or now it's already also called like conference. So we started this also maybe something like 7 or 8 years ago already. And there's the European Society for Thin Films, and they have some topical workshops every year on special topics. And at that time, they decided, we should do a workshop on ALD, so that's somehow an upcoming topic. And we did that. And typically they have workshops with, I don't know, maybe 20 people are joining or something, and then they have their break even, and then the conference fee is paying for most things, and then it's fine for them. And the first workshop was also something like 80 people joined, and we have been extremely happy about that, because we earned a lot of money, which was useful for financing the other stuff they are doing. And then they decided, okay, that's successful, we have to do this next year again. And they did that. And since then we have such a workshop every year. I think in between it was also somewhere else, not only in Dresden, but due to Corona, we switched back to Dresden. And since they are also from Dresden, it's easier for them to organize it here. It's more focused on industry, so industry topics, or how ALD is used in industry, so applications from industry. And it's also more from, let's say, an industry audience. So, for example, if a company is thinking about how can we use ALD, so just decide, okay, we spend some money for a conference fee and send somebody there so that he can learn something about ALD. So there's always a tutorial, so half a day, and then also see something about applications and how other companies are using ALD. And yeah, so that works also quite good. So the ALPIN workshop is more focused on, let's say, research groups and so on, but nevertheless there are still companies joining, which are interested in that, or also want to get in contact with new students maybe and things like this. And the ALD for industry is more industry focused, let's say. Yeah. So this is what I'm mainly involved. Besides
Yeah,
a lot of
I
other stuff.
I was at both of those events this year, both the ALD for Industry in March, and then Alpine, where we met in September. And yeah, they're really fantastic events. I mean, just thinking about 2 points that you made there. Yeah, the conference expenses are crazy. The ALD conference was in Washington State in the U.S. this year, and I mean, there were so few Europeans there, and it's I mean, it is a shame. And that one is Bellevue is so far away. I mean, it's about as far as you can go, other than Hawaii or Alaska in the U.S. So it's crazy. And then like having an industry session, I think is so like it's very brilliant, because I find that the industry sessions at the ALD conference are usually like the most well attended as well. So like a lot of people, I mean, both students that are interested in what companies are doing, and then other companies hearing what is due, and just in general, like having some idea of the entire breadth of topics that actually go into industry is very useful. I think you get, especially as a student, so focused on one thing, you forget that like once you leave academia and you go to a company, it's like there are so many other things that you're going to need to worry about. So.
Yes. So ALD is already involved in so many fields. I mean, of course, microelectronics is mainly a driver, and this is where it came from, or where it was used first in high volume production. But there are so many, or even small companies using ALD for some specific application and so on. So that it's of course interesting for them and also for other companies to see how ALD might help. And in my opinion, there are much more companies out there who might have some benefit of using an ALD process, and they are just not aware that there is some process working like that. So they have maybe some special parts, and this needs to be coded, and they just don't know that there's a process which is able to coat the inner surface of their parts or something like that. So that might happen. So I've been talking to people in the past who joined the ALD for industry workshops, for example, and said, so we just heard that there's a process like this. That's exactly what's interesting for us. I'm not sure if they use it now, but at least there was some interest, and that it might be a possibility for them. Maybe at the end they decide, okay, it's too slow, too expensive, whatever. But even there's a lot of progress ongoing in the last years, in my opinion. So the tools aren't that expensive, and the process is also not that expensive and that slow anymore. So that's why I think the field is growing, and more companies are using it. Yeah.
Well, it's good marketing for institutes like yourself as well, in case they need to do some proof of concept or some preliminary projects.
Yeah, of course. So we just started a project with a company, and we have in carbon-based membrane. So they call it graphene membrane, but it's multi-layer. So it's a carbon membrane, and this membrane needs to be protected against an oxygen plasma, because this is used in an environment where sometimes oxygen plasma is needed. And so we had to find a way to protect this from the plasma, but there are some more specific demands on the film, so it has to be really lightweight and thin and so on. And as most people know, it's hard to grow something on the graphene surface which is chemically inert, or should be like that. So you have to find some special tweaks to start your film growth and so on. So that's why there's a joint project, and to develop an suitable coating for them, and then it will be transferred to their production line, and then they will use it, I'm pretty sure, or they already are doing that, and we still want to optimize that. And
Speaking of some other things that you do for industry, we have a couple of topics still to go on here, but I think it's a nice segue into like that you have a company called
Yeah.
ALS Metrology, and
Yeah.
you talked a little bit about it at the ALPIN workshop, some of the
Yeah.
QCM work that you were doing. But yeah, I'd like to hear a little bit about where the inspiration for this company came and then what you're working on there.
Yeah, so it all started that we have, of course, research ALD tools, and they are customized, or at the beginning, and some of them even have been self-built. And so some, especially our biggest ALD tool, is really complex. So there are a lot of things which can go wrong, and they go wrong. And at the end, it's still a big black box. Yeah, so you put a wafer in, then you take a wafer out after the process, and maybe it's fine or maybe not. And you are wondering what was the reason why it's not working like this. And so there, even already at the beginning, there was some idea, okay, we have to find a way to have a look into the tool and see what's happening there. So we started with two methods. We at first used our ellipsometer and connected it to a tool. So we have some in situ ellipsometry possibilities with some purged windows and flanges. So we can do ellipsometry during the deposition of a film. And this is, of course, already really helpful to see how the film is growing. And you can, since ellipsometry is also very sensitive, you can do just a few cycles of any specific process parameter setup and then see, okay, film growth was like this, then you change something in your process, then you repeat a few cycles and so on. So that's extremely helpful to understand these processes. And we did this in the first chamber. And there was a second chamber, which I was using most. And there was no possibility to attach such an ellipsometer because, simply of the geometry of the tool, there was no space and so on, no possibility to do this. And then we saw in literature, of course, people are using QCMs to monitor such a film growth. And so then we decided, okay, that's might be a good option for that, and build something which could be installed in that process chamber to monitor the process. And then, of course, we had to learn a lot of things. So these QCMs are really temperature sensitive, and so you can, if you are doing it wrong, you can just do argon pulses, and it looks like a film deposition because of temperature changes and all these things. And I was having this as a side project all time and developing this further and further to monitor our processes. At that time, I was throwing that at conferences or workshops, and then often people came afterwards and said, "Oh, that's cool! And where can I buy such a system to monitor our process?" And I said, I built it everything by myself, and there are some special things like I'm doing some temperature compensation by using two crystals in parallel, and then you can calculate in signal without the temperature effect and so on. And so it was simply not available, something like this. And also the available QCM hardware, let's say, was not really useful for most ALD tools. So we started with something like this in one chamber at the beginning, and it was simply not possible because most of these QCM sensors are made for PVD tools, and then you just have a flange, put this QCM sensor in line of sight to your evaporation source in the PVD system, and then there's some condensation of material at the surface of the QCM. You can measure that, and that's fine. But in ALD, I mean, you want to have the same film growth on the QCM like on your wafer or on your samples, which means you have to have at least the same temperature on your QCM. You have the same gas flow to the QCM and so on. So somehow it shouldn't be a separate sensor which is somehow inserted in the tool. So I mean, often it's simply not possible because of the tool design, and even if it's possible, it's still often not a good way to do it like this. And then I developed something which more or less looks like a big wafer with QCMs. It's somehow the same film growth on the QCMs like on the wafer you put in the chamber. And in my opinion, this was the way to go to monitor exactly the film growth on this. And as I said, and people have been asking for that and how they can do it in their own lab and in their tools. And then they had to say, yeah, that's you cannot buy this, sorry. and then I decided, okay, so maybe let's found a small company. I mean, I know how to build these things and how to use them, and yeah, this was the starting point. And then I founded this company, and then sold some systems already. Yeah,
that's great. Yeah, I really like the QCM design, this QCM wafer, and I think people have this misconception that ALD is like always ideal, and that every every ALD tool is not built the same. You need to tweak a bunch of stuff, and it's not growing the same in every position in the chamber. So like you're totally right when you say it is a black box inside there most of the time.
So I'm really convinced of this because I know how these tools are working and the processes are working and what can affect your process. I mean, there are so many parameters affecting this, and I think most people are not really aware of this because they simply don't see these things. So they just say, okay, our film is now a little bit thinner than last time, and who knows? And if you are doing it, for example, with the QCM stuff and in more detail and faster, then you might start saying, so the bubbler fill level is affecting our dose. Of course, I mean, somehow this is clear, but then you can really see, okay, if I doing some control process which gives me a saturation curve. When I do this every week, then I can see, with the filling level of the bubbler, I can see how this saturation curve is stretching to longer pulse times or higher bubbler temperatures or something like this. So there are so many small things which can affect your process, and most of the time it might be okay since you are in this typical saturation, but there might be the point where your bubbler fill level, for example, is too low, and then you start being undersaturated, and then your film is simply not like it should be. And then without these special insights or the possibilities to obtain a saturation curve within a few minutes or something, you start doing test processes and trying to do this and this, and you're wondering what could be the reason for that and so on. So, and that's why I'm also really convinced of that, because I'm using it a lot, or we are using it a lot for even different tools for different purposes. It really helps a lot.
I think you need to find a PhD student who's really interested in microelectronics and also like business development. And you can task them with this.
So I tried this in the past. I already had two, and I thought I can convince them, but at the end both left and went to a big company paying a lot of money. But I have at the moment 2 PhD students and hope that there will be more, and they are interested, and they are also using, of course, the QCM stuff we have in our tools. They already know that it's helpful and that they want to use it.
I will also give a shout out to a former student of yours, Marcel, who became a postdoc in my group the last couple of years. I was in CU Boulder, and he started doing some MLD work and built a in situ ellipsometer tool to do it, and did some really great stuff with it.
So we shared an office many years, and he was also mainly responsible for our in situ ellipsometry stuff we are doing. So we have, as I said, we have one chamber with such an equipment, and it's also useful, of course. So, for example, for the already mentioned project on having a coating on this carbon film or carbon membrane, there, for example, we want to use the ellipsometer because we want to see the film growth, the initial film growth on the carbon surface, and that's of course something what you can do with the ellipsometer. Of course, we are also using like in vacuum XPS to see how much film material is chemisorbed after the first cycle or after the first pulse of precursor, and then how some pre-treatments can affect this and can be changing the amount of material and so on. So that's also something, especially so the initial film growth, which is very sensitive to a lot of things, and which is really hard to investigate if you don't have these in situ or at least in vacuum possibilities to do that. And of course, ellipsometer is really nice, and I like it. I use it a lot, especially as a ex situ ellipsometer, but of course also our in situ ellipsometer for some special applications. And I'm also convinced that this is a useful thing. But as I said, you cannot use this in every tool, and you can obtain a lot more information and data, but it makes it more complex. And you have to find a suitable optical model for your film, and this can be quite difficult, especially in the beginning, if you start growing some islands and maybe film properties are different than in a bulky material and so on. So you have to spend a lot of brain in that to have some useful information. So if you are able to do this, then it's really good. So with the QCMs, as long as you get rid of the temperature problems, by doing some compensation, then it's simply just mass uptake. You can just say, okay, there's a frequency change, so it means there's some mass attached to the surface. Both methods are fine. Yeah, and I know that Marcel is really experienced in that. So it was his main topic here. So he was mainly doing that.
We had an ex situ ellipsometer that we all knew how to use, but I think once Marcel came, our ability to get information out of it was really skyrocketed from that point.
Yeah.
So
yeah, that somehow became his passion. So he did it already in his diploma, and then he never stopped doing it. So as well as I'm addicted to QCMs, he is to ellipsometry.
It's great. You would love to work in the George labs. They also really love QCM in that lab as well.
I know. Yeah, I mean, that was our starting point, that we saw that some groups using this in a, let's say, really lab scale or self-built tool, and that's fine. I mean, there you can even find possibilities to use something like in standard QCM sensor, or you can easily build something by your own. But if you have a tool which is more like more similar to an industrial tool which is capable of coding 300 millimeter wafers, for example, like the tool we are using a lot, then you are simply not able to use a standard QCM stuff, and then you have to find some better solution.
I do want to talk about the specific research topic also that you work on, that we chatted a bit about on our last call, and that is the flash lamp annealing ALD, or FE-ALD, I guess flash lamp enhanced ALD.
Yeah, so we have different names for that. So depending on how you use it. So we started with that also many years ago. So we bought a tool which has the possibility of doing ALD, also some PCVD is possible, and some flash lamp annealing. And flash lamp annealing means you have a kind of window on top of your samples, and above this window there are some xenon lamps, and there are some big capacitors in our clean room basement, and some long cables and big cables, and then you can ignite light flash in these xenon lamps. So the flash itself is just 1.8 milliseconds in length, and so the light intensity is that high, since you are igniting them with 2.5 or 3,000 volts, so that you can heat up the surface of your sample or your wafer for 100, 200 degrees C. Strongly depends on the material and the wafer and some other stuff. So the first idea was to use this as a normal post-treatment, so having an ALD process and then doing some flash lamp annealing. So using it as a normal annealing step. And of course, this is somehow working, but it's not that useful, because you can also use an RTP tool or normal furnace or so. Also, maybe the different time scale of the annealing step might change something and might change film properties. But then, of course, we came up with the idea of, why not include the flash lamp annealing in every cycle? So then the first stuff was, or the first idea was to do, for example, aluminum oxide at a low temperature, but having this flash lamp annealing step in every cycle, or in every second cycle or third or whatever, and then checking the film properties. And we have been able to show that you can do a process as 80 degrees C, and with the flash in between, so in included in its cycle, or at least in every second cycle, we have been able to have the same film properties like density or refractive index, like we have if we did the process at 250 degrees C. So the flash lamp annealing was working, and was somehow useful, because, as I said, the temperature of the substrate was lower. Of course, you heat it up with the flash, but where you just heat up the surface, and most of the heat is spread into the bulk, and then the bulk itself will remain at a lower temperature, so the thermal budget is much lower. And so this was successful already. And then the idea came up, okay, so there are precursors which are used for CVD, so they are decomposed in the CVD process simply by thermal decomposition. But they are also used for ALD, so they have a self-limiting behavior if they are chemisorbing at the surface. So why not combine both? And then the idea was to have a precursor pulse coating the whole surface with precursor molecules, and then afterwards replacing the second reactant, like an oxidizing agent or some reducing agent, by using a flash lamp annealing step to thermally decompose the chemisorbed molecules. And also, again, this was also working. So we have been able to, for example, do a titanium oxide deposition using TTIP, so titanium tetraisopropoxide, which already delivers titanium atoms and oxygen atoms. So that was one of our first choices for that topic. So we have some self-limiting coverage of the surface, and then afterwards we did a flash lamp annealing step to decompose these molecules. And since this is a precursor which is also used for CVD, it was working fine, and the result was a titanium oxide surface. And then you can start over with the next cycle. The surface is reactive again for TTIP molecules, so you can coat them again with a whole layer of TTIP molecules, and then do the next flash lamp annealing step, and so on. And at the end, there was a titanium oxide film grown just with one precursor, so it's a single source process in combination with the flash lamp step. And we didn't have to use an oxidizing agent, for example, so which was the first idea to say, okay, we can grow an oxide film, but we don't have to use an oxidizing agent. Maybe that's helpful if you have an insensitive substrate material, which isn't, or it's very reactive with water or ozone or whatever. So you don't want to have some oxidizing agent. And of course, the overall goal is always to have a process for depositing metals or things which are more complicated to do with normal ALD processes. And so it's planned to have a joint project with Anjana Devi. She's developing precursors and so on. So the idea is to develop a precursor which can chemisorb in a self-limiting way, like a normal ALD precursor. And if you crack them by thermal decomposition, then the result is something like a metal film, something like this. Of course, there are some challenges to find something which decomposes to that film material and is still reactive for the next cycle or for the next precursor pulse. But that's what we think should be possible and will be somehow possible, or at least you can do maybe some nitride films or carbides or whatever with interesting film properties, or a better way of doing it, because you maybe don't have to use special plasma steps or so, and these things. And that's quite unique. So I don't think that somebody else has a tool like this up to now, which combines ALD and this flash lamp annealing. So it's interesting. Everything you try and everything you do is new.
Absolutely. I haven't seen it come up with anybody else other than your names. And it's, I think, a lot of like interesting implications. I was going to ask if you could take, some of these materials that typically you need to use plasma for because you can't get enough energy, and instead just do it with the flash lamp annealing. A question about that's interesting. If you are able to like replace plasma, of course, the whole downside people say for plasma is conformality. What is the ability of this to do like high aspect ratio stuff?
So we tried this, of course, and so the flash lamp is heating let's say the top microns of a silicon wafer, so maybe down to 5 microns or so. That's the the region or the volume where the flash lamp light is absorbed. And this is where you generate the heat. And we also did some experiments with structures, so 3D features like through silicon vias and so on. And I don't have the number right now, but we have been able to have in conformal coating at least to a few micron steps. So I cannot tell if it was 3, 5, or 10, I don't know. But it was possible to have with exactly this process with the titanium oxide, for example. We have seen in the SEM pictures in the cross section that there was the same film thickness at the top of the wafer, like maybe a few micrometers in the depth of the 3D feature. Yeah, of course, it's not like having a coating in the depth of 200 micrometers or something like this, what normal ALD should be able to do. So it's more surface process, but it works at least for some depth. Yeah. So conformality can be fine. I mean, the overall principle is that the first step, so the precursor step, is like in a normal ALD process, and it's self-limiting. So you can just have a big dose and deliver enough for coating the whole surface. And then the flash lamp step can decompose everything, so it doesn't need to be self-limiting, of course. It's just changing everything, but it's the same in most ALD processes. I mean, if you do a water step in an oxide process, the water will also oxidize everything and it wouldn't stop on the surface maybe. But since there's just one layer which can be oxidized, it's ALD. And so with the flash lamp based process, it's the same. Sometimes we even have to do multiple flashes. So for some specific precursors, maybe our maximum flash light intensity is not sufficient. Or if you want to reduce the workload for flash lamps or something like this, then we can also do a lower energy but multiple flashes, things like this. And yeah, so the tool is of course also a prototype. So if you want to use this on bigger scale substrate and things like this is also possible. I mean, there are groups using flash lamp annealing in different fields, let's say, not for ALD related topics, and also on bigger sizes. I mean, also in microelectronics industry, I think flash lamp annealing is used to do some dopant activation or things like this. So people are using this on 300 millimeter wafers and so on.
Yeah, that's fantastic. It's very cool. I think. And is there a chance that this could be scaled to something like a batch tool or like maybe a spatial kind of configuration?
So I think it wouldn't be possible for a batch tool, since you always have to have this line of sight between your flash lamps and your wafers. So it will be always something like single wafer tool. But or the spatial stuff is also possible. So we have been in contact with a company in the past where they did coatings on very big glass substrates, so meter scale stuff. And we have been using flash lamps, a row of flash lamps or more of them, more rows, to do this annealing of these substrates. So, and this was some kind like a spatial process. So the substrate was moving underneath the flash lamp, and the flash lamp has been igniting their flashes something like 10 hertz, so 10 times a second, and the substrate was going underneath and was heated in every area of the substrate. So in principle, of course, this is possible. Yeah. So I mean, we have to do our stuff first and have to develop useful processes and do the proof of concept and how it should be done. And then maybe, that's also an idea to use this in a spatial tool, to have some annealing step in between. So very short annealing step with low thermal budget, but still improving film properties or changing something at least. Should be possible.
Great. Sounds like there is some kind of roadmap for this technology then.
Yeah, somehow.
Yeah.
Yeah.
Oh, good. That's fantastic. Martin, this has been really, really great. We've had pretty deep conversation here about a lot of topics in an hour.
Yeah.
Do you have any parting words as we finish up here for people in ALD, microelectronics? Anything you'd like to, any wisdom you'd like to lay for us?
Wow, that's That's difficult. I mean, everybody should know now that they have to use QCMs. I hope so, at least. Yeah. No, yeah. So I'm still convinced of that topic and ALD. So it's a growing field and it's interesting. So I'm happy about everybody who is related to this and it's interested in ALD and doing research on that. And yeah, so I'm looking forward to meet most of you, all of you, next time at the next workshop, next conferences, talk about everything. Yeah, and also looking forward to the next podcast and let's see what other people are talking about and so on.
That's right. Last Thursday of every month, if people who are listening don't know that yet.
Okay.
Well, very good. Thanks a lot, Martin, for joining me today. This was really, really quite nice. And yeah, I'll probably look forward to seeing you at whatever German community ALD event that is happening next. So.
Okay, yeah. So you're welcome, and thank you for asking me for having this conversation. It was interesting. I'm looking forward to the podcast and also to the next one, as I said. So
great.
Cool.
Awesome. Great. Thanks, Martin. Take care.
Okay, you're welcome. Have a nice week.
Thanks for listening to ALD Stories with Benek. To stay updated on new episodes each month, please follow us on Spotify, Apple Podcasts, or Google Podcasts. We hope you enjoyed the show. I hope to see you again in the next one.